Something huge is sliding through the outer darkness toward our Sunday. It is not a flashy bullet, just slow and inevitable. Astronomers call it Comet Bernardinelli Bernstein, a frozen relic of formation. Its nucleus is around 137 kilometers wide. That makes visitors like Oumuamua or Three-Eye Atlas look tiny. It has fallen inward for ages from the outer cloud. We only recognized it recently in old survey images. By the end, you will see why this giant might rewrite our picture of the solar system. So tap like, hit subscribe, and come with me into the dark. Imagine you are an astronomer who spends a career studying comets. You watch small, icy bodies sweep in from the outer reaches, flare near the sun, then fade back into the black. You know their behavior. You know their usual sizes. Most are a few kilometers across, maybe 10 if you are lucky. Interesting, beautiful, but small. In that world, a 130-plus kilometer nucleus is not just big, it is a problem. The story of Bernardinelli Bernstein begins quietly, deep in the data archive. Between 2013 and 2019, the Dark Energy Survey mapped the southern sky again and again, hunting for clues about cosmic expansion, not comets. Years later, two researchers reprocessed those images, looking for moving dots. One faint speck shifted against the background stars in just the right way. At first, it looked like just another distant object. Nothing urgent, no alarm bells. Then the team calculated the orbit and brightness more carefully. This thing was far away, far beyond Saturn, yet brighter than it should have been at that distance. As more images were linked together, the apparent motion traced out an enormous ellipse around the Sunday. The designation came first, the usual string of letters and numbers, C2014UN271. The human name followed, Bernardinelli Bernstein, after the two people who pulled it out of the noise. The more we measured, the stranger it looked. Using the Hubble Space Telescope, astronomers tried to separate the fuzzy coma from the solid nucleus. After careful modeling, they estimated a chunk of rock and ice, perhaps 120 to 150 kilometers wide. That is roughly the distance a jet would cover in an hour at cruising speed. It is larger than many known moons. It is several times the size of typical comet celebrities like Halley. In terms of mass, it could be 10,000 times heftier than a small comet from the inner cloud. Comets are supposed to be the crumbs of planet-making. They are leftovers, icy rubble that never grew big enough to become worlds. Our standard picture says they formed as loose piles of ice and dust, gently glued together, drifting beyond the giant planets. A body as large and smooth as Bernardinelli Bernstein does not fit neatly into that category. Its gravity is strong enough to pull itself into a rounded shape. Its interior may have layered over time. That makes it feel less like a crumb and more like a half-finished world that was thrown out of the kitchen. Where did it come from? All signs point to the distant cloud that surrounds our system like a shell, a reservoir of trillions of icy bodies that stretches almost a light year from the Sunday. For billions of years, Bernardinelli Bernstein likely moved through that deep freeze, far beyond the reach of any telescope on Earth. Out there, the sun is just one bright star among many. Orbits take millions of years. Changes are slow. Objects are supposed to sleep. Yet this one woke up. One of the first clues that something was off came from simple brightness measurements. Bernardinelli Bernstein was already active long before it reached the realm of the giant planets. Normally, comets begin to vent water vapor when they get near Jupiter and Saturn, where sunlight is strong enough to warm their surfaces above the deep freeze. But this object was brightening even farther out, at distances where water ice should be rock hard. Like a freezer that starts to fog before you open the door, it glowed when models said it should stay dark. Later, radio observations would reveal carbon monoxide jets as the likely cause, but even before that, the behavior hinted at a huge internal supply of very volatile ices. That, in turn, implied a different kind of history. Bernardinelli Bernstein had stayed so cold for so long that delicate molecules survived untouched for the entire age of the solar system. As it drifted inward, those stores began to leak, turning the comet into a slowly breathing thing long before its real show near perihelion. Then there is the timing. For most of human history, we had no idea such giants existed. Only in the last decade have sky surveys become sensitive enough to spot faint moving objects in the outer dark. In roughly the same window, we have watched interstellar objects like Oumuamua and Borisov sweep through, and we have begun to suspect that the distant cloud may be more crowded and more dynamic than our textbooks suggested. Bernardinelli Bernstein arrives right into that moment of doubt, as if on cue. Of course, there is no script, no cosmic storyteller choosing dramatic entries. Yet it is hard not to feel a little targeted when the biggest comet nucleus ever seen chooses to swing inward exactly when we finally have the tools to notice it. If our instruments had been slightly worse, this giant would have passed unnoticed, a ghost in the dark. Instead, we see it, and now we have to explain it. So this is where we stand. A body the size of a small city-state, heavier than 10,000 familiar comets glued together, has been dislodged from the deepest reservoir around our sunday. It is active at distances where comets should sleep. Its sheer scale hints at planet-building and planet-breaking events in the young solar system that we still do not fully understand. And we have caught it in the act, halfway between eternal sleep and its one close brush with sunlight. The obvious question is simple and unnerving. What pushed something this massive out of its ancient orbit? In the next part, we will follow that question back into the dark and ask what kind of forces can wake a giant like this from a billion-year sleep. Picture the solar system not as a flat map with neat planet orbits, but as a tiny glowing core wrapped in a vast invisible shell. That shell is the outer cloud. It begins far beyond Neptune and stretches almost a full light year into space. Out there, the sun is just one bright point among many. Its gravity is weak. Orbits take millions of years. Nothing happens fast. In that region, ice is king. Comets are deep frozen time capsules, locked at temperatures close to absolute zero. They drift slowly on elongated paths, barely moving against the starry background. For billions of years, a body like Bernardinelli Bernstein could circle the sun once or twice and never come close to the planets. In most models, these giants are museum pieces preserved in place. They are not supposed to get stirred very often. So when we say Bernardinelli Bernstein has been falling inward for a long time, we are really saying something disturbed it. Something nudged a stable orbit just enough that, over countless loops, the path elongated until one end dipped closer and closer to the sunday. On human timescales, that looks like a sudden awakening. On cosmic timescales, it is a slow-motion slide that began ages ago. The puzzle is what started the slide. One idea points to the galaxy itself. Our solar system orbits the center of the Milky Way, plunging in and out of the galactic plane like a slow pendulum. The combined gravity of stars, gas, and dark matter creates what astronomers call galactic tides. They are like ocean tides on Earth, but operating on clouds of comets rather than on water. When the sun passes through certain regions of the galaxy, these tides grow stronger and can tug on the outer cloud. In some models, those tides do not pull steadily. They pulse. Roughly every tens of millions of years, the geometry lines up in a way that delivers a stronger kick to the distant cloud. A wave of comets is shaken loose. Most are small, a few are huge. Bernardinelli Bernstein could be one of those. A giant that started drifting inward long before humans evolved, the delayed result of a past galactic tide peak. Another suspect is a passing star. The sun was born in a crowded stellar nursery. Even today, as we travel through the galaxy, other stars occasionally pass within a few light years. That is far from our inner planets, but uncomfortably close to the outer cloud. A star with even a fraction of the sun's mass, sweeping by at a few thousand astronomical units, can stretch and twist the orbits of distant comets. Missions like Gaia have mapped the motions of nearby stars with exquisite precision. When dynamicists roll the clock back in their simulations, they see hints of past close encounters. A star brushes by. The cloud ripples. Some objects are flung out into interstellar space. Others are nudged inward onto long, slow dives. If Bernardinelli Bernstein began its inward journey because of such a visit, then we are watching a story that started hundreds of millions of years ago finally play its last act. There is also the quieter view. No big event, no dramatic encounter, just gravity doing what gravity does. Even in a calm outer cloud, objects tug on one another very gently. Over billions of years, those tiny pulls add up. Orbits drift. Some become slightly more elongated. Some tilt. A few wander just far enough from perfect balance that they start to fall toward the Sunday. In that picture, Bernardinelli Bernstein is the outcome of cosmic patience rather than cosmic violence. Yet many astronomers feel that explanation is a little too neat when you look at the specifics. This is not a modest ice ball, but one of the largest comet-like objects ever seen on a path that slices the planetary system almost at right angles. Its inward arrival happens to coincide with an era when we are suddenly seeing interstellar wanderers and unusual comets at a rate that makes statisticians frown. At some point, coincidence begins to look like a pattern. That suspicion has fueled more speculative ideas. Perhaps there is a hidden massive body far beyond Neptune, a planet-sized object, or a cluster of smaller objects whose collective pull occasionally stirs the outer cloud. Perhaps there are dense clumps of dark matter drifting through the galaxy, invisible yet massive enough to jostle distant comets when they pass by. These notions are not proven. They are attempts to explain a feeling that the outer reaches of our system are more lively than our simple models predicted. Whatever the cause, the consequence is clear. Bernardinelli Bernstein is now on an inbound leg of a huge orbit. For ages, it barely noticed the Sunday. Now, each year, the sunlight grows slightly stronger. Deep frozen ices begin to warm. Hypervolatile molecules like carbon monoxide start to seep out through cracks in the crust. The giant that slept in darkness is slowly, silently waking up. That is not just an interesting detail. It is a warning. If one giant can be shaken loose, others can too. The outer cloud likely holds countless objects of similar or greater size. Most will never come close enough to matter to us. But the same unknown forces that change this orbit could, over long times, send another giant on a path that crosses not just the realm of Saturn, but the realm of Earth. For now, Bernardinelli Bernstein is not a threat. Its closest approach will stay near the orbit of Saturn. Yet, the mystery of what woke it touches something deeper. Our ability to predict the future of our solar system depends on understanding the processes that disturb the outer cloud. If we do not know what nudged this giant, we cannot be sure what other stories are already in motion beyond our sight. In the next part, we will stop looking at the wake-up call and look instead at the path itself. Because hidden inside Bernardinelli, Bernstein's orbit is another unsettling clue. This thing is not just coming in. It is coming in on a path that slices straight through the solar system from above, almost like it was dropped in from a different world. Orbits are like handwriting. Every loop around the sun encodes a little of an object's past. When you line up those loops for the planets, asteroids, and most comets, you see a pattern. Almost everything moves in the same flattened disk, a thin cosmic record where nearly all the tracks lie within a few degrees of one another. That disk is the plane of the solar system, the ecliptic. It is the fossil of the spinning cloud of gas and dust that formed the sun and its worlds. Bernardinelli Bernstein ignores that script. When astronomers solved for its orbit, they found that the plane of its path is tilted almost 95 degrees relative to the ecliptic. The planets are running laps on a racetrack. Bernardinelli Bernstein is diving through the stadium from the upper stands, threading the track at a steep angle. It is not coming in behind the plane of the solar system or ahead of it. It is slicing across it. That strange tilt matters. In a calm disk of formation, objects inherit similar inclinations. To knock something into a near perpendicular orbit, you usually need violence. A strong gravitational encounter that kicks it out of the original plane. A close pass by a giant planet. A shove from a passing star. Or a complicated combination of many small tugs spread over deep time. One family of models paints the outer cloud as pure chaos. Over billions of years, passing stars and galactic tides have stirred that region like a pot of soup. Orbits get twisted, flipped, randomized. By now, in that picture, objects move on paths with every possible tilt. High inclination is not surprising. Bernardinelli Bernstein would simply be one of many. a natural byproduct of cosmic roughhousing. There is another possibility: capture. The early sun did not form alone. It was born in a cluster, surrounded by siblings, other stars with their own budding planets and clouds of debris. In those crowded conditions, objects can be traded. A comet that once orbited a different star can drift close enough to feel the gravity of the young sun and be stolen. Its old orbit is erased. A new gigantic orbit around our star is written instead. If Bernardinelli Bernstein began life around another star, its odd inclination would make sense. It would not reflect the flat disk that formed our planets. It would remember the geometry of a different system entirely. After capture, billions of years of slow perturbations could stretch that orbit into the extreme path we see now. In that story, Bernardinelli Bernstein is not just a fossil of our own formation. It is a refugee carrying the chemistry of somewhere else. Right now, we have no direct proof of capture. The orbit is bound to the Sunday. It is a stretched ellipse, not a one-time flyby like truly interstellar objects such as Oumuamua or 3I Atlas. But bound does not mean native. It only means that at some point in the past, the sun's gravity won the tug-of-war and kept it. The shape and tilt of the orbit also change how Bernardinelli Bernstein interacts with the rest of the solar system on this inbound pass. As it descends toward perihelion, it will cross the orbital planes of the giant planets. Each crossing is a chance for a small additional nudge. Saturn, Jupiter, even Uranus and Neptune can tweak the path slightly with their gravity. Most of those tugs will be tiny, but over millions of years they can add up to big changes when the comet climbs back outward. Celestial mechanics has a concept called resonance. When two bodies circle a central mass in periods that are simple ratios of one another, they can exchange energy in a steady, rhythmic way. Over long times, that rhythm can carve gaps in asteroid belts, pump up orbital eccentricities, and lock in patterns. If Bernardinelli Bernstein spends enough time with an orbital period related to that of one of the giants, the planet's gravity could sculpt its path in ways that are hard to undo. All of this makes the distant cloud less like a quiet reservoir and more like a vast pinball machine. Bernardinelli Bernstein is one of the balls. It was launched long ago by some combination of tides, stars, and planets. Now it is rolling through the inner parts of the machine, crossing the tracks of the giants, feeling their pulls, giving them tiny pulls in return. After this encounter, its path will be different forever. Some researchers find one detail especially unnerving. When they run many random simulations of bodies in the outer cloud, only a tiny fraction end up with orbits that match both the tilt and distance of Bernardinelli Bernstein. It is not impossible. It is just rare. That rarity fuels talk of hidden sculptors. Maybe there is a massive planet or a disk of smaller icy bodies beyond Neptune that has quietly pumped a subset of objects into steep, long-period orbits like this one. Others argue we may be falling for the oldest trap in statistics, focusing too much on the weird thing we noticed and forgetting all the other things we did not. In a cloud of trillions, some orbits will be extreme, simply by chance. We are paying attention to Bernardinelli Bernstein, precisely because it is odd. In that view, the orbit is a reminder that rare does not mean impossible. It does not require a secret planet. It just requires patience. Either way, the orbit is not just a line in a database. It is a story. A story that begins in the distant cloud, far beyond where our planets roam. A story that likely passes through encounters with stars, with the galactic tide, with the giant planets of our own system. And now that story is intersecting ours. We have talked about where Bernardinelli Bernstein might have come from, and how its path through space became so strange. Next, we dive inward, past the orbit and down into the body itself, to ask what kind of object can survive that long in the dark and still unleash powerful jets from its surface the moment sunlight returns. From far away, Bernardinelli Bernstein looks simple. A fuzzy dot with a faint tail, just another comet. The real shock comes when you try to imagine what is inside that dot. We cannot crack it open. We cannot send a drill. All we have are photons and a lot of patience. Yet even with that limitation, the picture forming inside this object is far stranger than anyone expected. The first big clue came from the Hubble Space Telescope. Hubble cannot resolve fine surface details at those distances, but it can separate the bright surrounding haze from the central core. When astronomers modeled the light, subtracted the coma, and isolated the nucleus, something surprising emerged. Bernardinelli Bernstein is not a jagged, potato-shaped lump. It is nearly spherical. Smooth. Uniform. Small comets do not look like that. When we have flown past them with spacecraft, they resemble misshapen rubble piles. They are stitched together from boulders and dust, held only lightly by weak gravity. Bernardinelli Bernstein is different. To pull itself into a sphere, its gravity had to be strong enough over time to pull material inward, to soften the edges, to iron out the big bumps. That points to a body with real internal structure, not just a loose pile of chunks. In planetary science, there is a threshold where gravity wins over rigidity, and objects relax into roundness. Worlds that cross that line can start to behave like tiny planets. Dense material sinks inward, lighter ices float upward, layers form. The nearly spherical silhouette of Bernardinelli Bernstein hints that it may have crossed at least partway over that line. It may have an outer crust, an icy mantle, and deeper pockets of different material arranged in shells. Radio observations added a second, even more important clue. In the high desert of Chile, the Atacama Large Millimeter Array turned its many dishes toward this distant visitor. Instead of just seeing a bland blur of cold dust, it picked up distinct emissions from carbon monoxide gas. More than that, it mapped where the gas was coming from. Not everywhere. Specific regions. Persistent jets. Carbon monoxide is what astronomers call a hypervolatile. It turns directly from solid to gas at extremely low temperatures, far colder than water ice can tolerate. The fact that Bernardinelli Bernstein is venting carbon monoxide strongly, while still tens of astronomical units from the Sun, tells us it holds vast internal stores of this fragile ice. Most comets lose these early in their lives. This one somehow kept them bottled up for billions of years. To explain that, researchers have proposed a layered chemistry model. Picture the interior of Bernardinelli Bernstein like an onion. The outermost rind is a crust of darker, tougher material. Below that is a region rich in water ice mixed with organic molecules. Deeper still lies carbon dioxide ice. Beneath that, in pockets and veins, lie reservoirs of carbon monoxide and other extremely volatile compounds. Each layer formed at a different temperature in the early solar system, and each layer wakes up at a different distance from the sunday. As the comet drifts inward, sunlight slowly works its way down this stack. First, only the most delicate ices near the surface respond. Carbon monoxide begins to sublimate through any cracks it can find. That is the stage we are in now. Later, as the comet gets closer, less volatile ices will start to warm. Water will join the outflow. The coma will grow thicker. The jets will change character. The whole behavior of the object will evolve as if someone is turning a hidden dial. There is another twist. Some laboratory work suggests that certain gases can be trapped inside special crystalline forms of ice. At very low temperatures, those crystals can lock gas in place for eons. Warm them just a little, and the crystals rearrange, suddenly releasing their trapped cargo. If Bernardinelli Bernstein contains such phase-trapped volatiles, we would expect gas to erupt from specific depths at specific temperatures, almost like underground pockets popping one by one. Mechanically, that is a recipe for stress. Gas building up under a rigid crust can fracture the surface. Cracks open, fissures widen. Those fissures become jets, focused nozzles that blast material into space. Over time, as more gas escapes, the internal pressure drops, and the vents can shut down, while new ones open elsewhere. The crust may sag or collapse above old voids. In extreme cases, whole blocks can break off. On small comets, this process produces chaotic, flickering behavior. Jets turn on and off. Rotation speeds change. Pieces split away. Bernardinelli Bernstein seems calmer. Its carbon monoxide jets appear in consistent regions and remain active over long stretches of time. That does not make it artificial. it makes it organized. It hints at a more coherent internal plumbing system, shaped not by a few random cracks, but by a long history of slow heating, freezing, and refreezing. That picture starts to sound less like a simple comet and more like a scaled-down icy moon. Many moons in the outer solar system show evidence of cryovolcanism, eruptions of cold material driven by internal heat. Their engines are tidal flexing or radioactive decay in rocky cores. Bernardinelli Bernstein is too isolated for tides, so if it has anything similar, the driver would be slow radioactive heating inside whatever rock it contains. Over billions of years, even a little of that heat can rearrange an interior. If this is right, Bernardinelli Bernstein is a hybrid. It behaves like a comet on the outside, with a coma and jets and a long eccentric orbit. On the inside, it may be more like a dwarf planet embryo, a nearly round body with layers, faults, and evolving internal chemistry. That hybrid nature matters because it means the show near perihelion could be much more dramatic than a simple scaling up of a normal comet. Layers might peel, jets might reroute, surface regions might collapse or flare in ways we have never seen. The classification questions may sound academic, but they drive real decisions. If we treat Bernardinelli Bernstein as just a big comet, we might settle for a few distant observations and move on. If we treat it as a missing link between comets and icy worlds, then suddenly it becomes a prime target for missions, a key data point for how planets grow and how the distant cloud is built. For now, all of that complexity remains hidden under hundreds of meters, maybe kilometers, of ancient ice and dust. Our best telescopes can only hint at the interior through its surface activity. And that activity is about to change much faster as the comet enters warmer regions. In the next part, we will step back from the structure and look at the timeline. The slow but urgent countdown as Bernardinelli Bernstein glides inward, and our chance to see its original self begins to evaporate. Imagine a skyscraper made of dirty ice gliding through space. It is not racing. It is drifting. Yet every year that passes, the physics inside that skyscraper changes. That is Bernardinelli Bernstein. On human timescales, it feels frozen in slow motion. On scientific timescales, the clock is ticking fast. Our chance to see it in anything like its original state is already slipping away. When astronomers first noticed it in dark energy survey data from the middle of the last decade, the comet had already been on its inward journey for a very long time. Its orbit reaches out into the distant cloud and loops back in over millions of years. The fall that we are watching began long before telescopes, long before cities, long before our species understood what a comet even was. We just happened to join the story near the end of one of its gigantic circuits. Right now, Bernardinelli Bernstein is still far from the Sunday. During recent observations, it sat around 16 to 18 astronomical units away. Neptune circles at about 30 astronomical units, Saturn around 9.5, Jupiter near 5. So this giant is threading the outer neighborhood between Neptune and Saturn, slowly drawing closer. Its motion is steady, but not dramatic, a few kilometers per second relative to the Sun, yet over the course of a year that adds up to hundreds of millions of kilometers covered. We know roughly where it is going. By the early 1930s, specifically around January of the year 2031, Bernardinelli Bernstein will reach its perihelion, the closest point to the Sun on this pass. That closest distance will be just under 11 astronomical units, slightly beyond the orbit of Saturn. It will never come anywhere near Earth. It will not slice through the inner planets. For planetary safety, this is a benign event. For science, it is a gold rush. The reason is simple. As the comet approaches the Sun, its surface and subsurface layers will be driven through a series of temperature thresholds. Right now, at large distances, carbon monoxide and other very volatile ices are doing most of the work. They are the ones turning to gas and venting through cracks. Closer in, water ice will begin to join them. When that happens, the coma will swell and thicken. Dust will flood out. The nucleus will be wrapped in its own exhaust. From a telescope's point of view, that is both beautiful and frustrating. A bright active comet is spectacular. It is also hard to see through. The sharp boundary of the nucleus blurs into a glowing cloud. Subtle clues about shape, rotation, and surface structure get smeared out. If you want to study the interior architecture of Bernardinelli Bernstein, your best chance is before the coma becomes overwhelming. That means the next few years, not the last few months before perihelion. Astronomers know this, which is why the object now competes for time on some of the most powerful instruments we have. Hubble is watching its brightness and coma shape. Radio arrays listen for the signatures of different gases. Large optical telescopes track small changes in spin and activity. Future observatories, including next-generation survey telescopes, will add even more eyes to the effort. Every new data set is like one more medical scan of a patient whose condition is changing every visit. There is another layer of urgency. Some comets do not survive their close approaches. As internal pressures rise and venting patterns shift, stresses can build. If cracks link up and weaknesses align, the body can fragment. That does not mean a Hollywood-style explosion. It can mean a slow unzipping. Large pieces peel away, exposing fresh interior ice that rapidly vaporizes. For Bernardinelli Bernstein, whose gravity is strong and size is immense, most models suggest stability. Still, with layered structure and deep volatile pockets, we cannot rule out partial shedding or reshaping. If it does fragment, the event would be both a loss and a gift. We would lose the chance to study a single intact giant nucleus. At the same time, we would gain a direct look at interior layers that no drill could ever reach. Different fragments might show different compositions, like broken pieces of a geological core sample scattered through space. Telescopes would be able to watch those fresh surfaces evolve in real time as sunlight hits ices that have been sealed away since the birth of the solar system. Even if it stays together, Bernardinelli Bernstein will become a more familiar presence as perihelion draws near. By 2030 or so, it may brighten enough that serious amateur astronomers with decent telescopes can pick it out in the outer sky, not a naked eye marvel, hanging over cities, but a faint ghost that anyone determined enough can hunt down. The idea that people in backyards could watch a small moon-sized comet glowing near the orbit of Saturn is extraordinary in itself. After perihelion, the story winds down quickly on human timescales. The comet will begin its long climb back outward. Activity will fade as it returns to colder regions. Its orbital period is measured in millions of years. Once it leaves the realm where we can study it easily, it will not return for longer than our species has existed. This is the only pass through the outer planetary region we will witness. For all practical purposes, we get one shot. That combination of slow motion and one time only is what makes Bernardinelli Bernstein feel so urgent. We have enough time to prepare observations, to coordinate instruments, maybe to dream about missions. We do not have enough time to waste years debating whether the object is interesting. It already is. The real question is what else it might be telling us about the population it came from. Because Bernardinelli Bernstein is not falling inward alone. In the last decade, a handful of other strange visitors have appeared on the charts, each carrying its own set of anomalies. In the next part, we will step back even further and ask whether this giant is part of a larger pattern, a sign that something has been shaking the outer reaches of our solar system more strongly and more recently than we ever imagined. Patterns are the universe tapping us on the shoulder. One odd object can be a curiosity. A string of them starts to feel like a message. Bernardinelli Bernstein would already be remarkable on its own. Yet it is arriving in a decade that has become suspiciously crowded with strange visitors. The question is whether we are just finally opening our eyes, or something out there has turned up the volume. Roll back to 2017. Astronomers scanning the sky notice a tiny object moving too fast, and on too open a path to be bound to the Sunday. We named it Oumuamua. It showed no obvious coma, no clear jets, yet its trajectory bent in a way that suggested some gentle, non-gravitational push. It was small, dark, elongated, and completely gone before we knew what to ask it. 2 years later, another outsider swept through. Comet Borisov was clearly interstellar. It had a bright coma and tail, and its chemistry looked almost comfortingly familiar. Water, carbon monoxide, cyanide compounds, the usual comet recipe. In one sense, that made it less dramatic than Oumuamua. In another sense, it was more profound. It hinted that whatever processes build comets around other stars are not entirely alien to ours. Then came 3I Atlas, another interstellar interloper much talked about for its own oddities. Small, fast, fragile, loaded with puzzles about composition and behavior near the Sunday. Each of these objects snapped into view for a brief time, dumped a pile of questions on the desk of every dynamicist and comet physicist, and then raced back into the void. Now we have Bernardinelli Bernstein. Unlike those hyperbolic visitors, this one is gravitationally bound to the Sunday. It belongs to us in a way they never did, yet in terms of mass and scale, it makes all of them look like gravel. If you line up the cast list for the last 10 years, you see an interstellar shard that breaks rules, an interstellar comet that confirms some rules, another odd traveler from beyond, and a homegrown giant sliding in from the distant cloud. The simplest explanation is technological. Our surveys have gone from narrow, deep snapshots to wide, continuous monitoring. Telescopes like Pan-STARRS, the Dark Energy Survey, and newer facilities scan huge patches of sky every clear night. Better hardware and software mean we detect faint, fast-moving objects that older surveys would have missed completely. Under that view, nothing cosmic has changed. Only our perception has. To test that idea, researchers build population models. They estimate how many interstellar objects should wander through a volume the size of our solar system, based on stellar densities and typical speeds. They fold in the sensitivity of current surveys and the geometry of the sky coverage. Then they ask how often an object like Oumuamua or Borisov should be spotted. Those calculations say we should see some. But the exact recent lineup stretches those expectations. Not wildly, just enough to make the statistics feel sticky in the teeth. A similar exercise plays out for long-period comets and outer cloud giants. How often should a Bernardinelli Bernstein-sized object drop into the outer planetary region on a path our telescopes can see? Again, the answer is not never. The cloud is huge. Given enough time, almost anything that can happen will happen. Yet when you factor in survey coverage and detection limits, catching one in this particular technological window begins to look a little lucky. Maybe we are lucky. Or maybe we are in the crest of a broader wave. Some dynamicists have run simulations of the outer cloud under different kinds of disturbances. They add a passing star at a certain distance. They add a stronger than usual episode of galactic tides. They add, in some runs, a massive unseen perturber beyond Neptune. In many of those scenarios, inward comets do not trickle in smoothly. They arrive in pulses. For tens of millions of years, the cloud is quiet. Then a disturbance sends a flurry of bodies inward. Big ones, small ones. A whole swarm slowly cascades toward the inner system. On geological timescales, these pulses could line up with impact episodes on planets, spikes in crater records, maybe even extinctions. On human timescales, they look like a handful of weird objects turning up in the same century. Oumuamua, Borisov, 3I Atlas, Bernardinelli, Bernstein, and likely others we have not fully recognized. If that is what we are seeing, then this is not just a random collection. It is the visible tip of a long, slow avalanche that started with some event far away and long ago. Of course, there is a danger in chasing patterns. Our brains are tuned to connect dots, sometimes too eager to find order in noise. Point to any decade in the history of comet discovery, and you can highlight a few standouts, then spin a story about why that decade was special. That is why scientists lean so hard on models, statistics, and blind tests. They want to know whether the cluster of anomalies we are excited about really is unlikely, or merely feels that way. Right now, the verdict is unsettled. Some analyses suggest the recent run of strange visitors is well within the range of chance once you account for better sky coverage. Others hint that there might be a modest excess that points to something more. What everyone agrees on is that the outer solar system is more dynamic than the tidy diagrams in textbooks implied. Things are being stirred. Bodies are being nudged. Giants are waking up. Bernardinelli Bernstein becomes, in that context, more than a single specimen. It is a test of whether our models of how comets are injected into the inner system are complete. It is a chance to see whether the same physics that explains Oumuamua and Borisov and the long-period comet population can also explain a 100-plus kilometer hybrid world on a steep inclined path. If the answer is yes, then our strange recent decade was simply the moment we finally built good enough eyes. If the answer is no, then we are missing something big, some extra tug, some hidden structure, some piece of the gravitational puzzle that keeps pushing ice giants out of the dark and into the light. In the next part, we will look more directly at those invisible hands, from proposed hidden planets to clumps of dark matter and the ghostly tides of the galaxy itself, and ask what, if anything, could be out there sculpting the paths of objects like Bernardinelli Bernstein from behind the scenes. If Bernardinelli Bernstein is a pinball, something had to tilt the machine. The orbit is steep, the timing is odd, the object is huge. When you put all of that together, it is hard not to ask whether there is an unseen player at the edge of the board. Over the last decade, astronomers have been quietly arguing about what that unseen player might be. A hidden planet, a massive disk of icy bodies, clumps of invisible matter, or just gravity playing long, slow tricks at scales we have not fully appreciated. The most famous suspect has a name that sounds like a ghost story: Planet 9. The idea surfaced when researchers noticed that several distant trans-Neptunian objects shared a strange alignment. Their closest approach points to the Sun, clustered in the same region of space. In a random cloud, those angles should smear out. Here, they seem to point the same way, as if something massive were hurting them. The simplest explanation was a planet several times, heavier than Earth, far beyond Neptune, on a stretched and tilted orbit of its own. In this picture, Planet 9 is a bully in the dark. It never comes anywhere near the inner planets, but its slow, persistent pull sculpts the orbits of objects in the distant disk and cloud. Over millions of years, it can pump some bodies into higher inclinations, stretch their ellipses, and occasionally send one over the edge into a long plunge inward. Bernardinelli Bernstein could be one of those victims. Its steep orbit and huge size, a calling card from a world we have yet to see. The trouble is that seeing it has proven brutally hard. Astronomers have combed the predicted regions of sky with large telescopes, searching for a faint, slow, moving point of light. Survey after survey has turned up nothing that clearly fits. That does not kill the hypothesis. A planet that distant could be much dimmer than expected. It could be hiding in a crowded star field. It could be in a part of the sky our surveys have not yet covered deeply. But every null result tightens the corner it can hide in and makes some people wonder whether the pattern that inspired the idea was a statistical mirage. In response, other models stepped in. One alternative replaces a single hidden planet with a broad disk of smaller bodies beyond Neptune, carrying enough total mass to behave almost like a continuous medium. In that scenario, the collective gravity of countless icy fragments can subtly reshape orbits in the outer system. Clumps form, gaps appear. Some objects get nudged into strange inclinations. No single Planet 9 required. Just a vast, unseen belt checking the motion of anything that strays too close. Then there is the truly invisible candidate, dark matter. For years, we treated the dark matter halo of our galaxy as a smooth background, a gentle fog of unseen mass. More detailed work suggests that halo might be granular instead. If dark matter forms dense streams and clumps, those clumps could drift through the outskirts of the solar system like ghostly asteroids. Their gravity would be weak compared to a star or a planet. But over millions of years, even a soft tug can shift the path of bodies in the distant cloud. Imagine a dense patch of dark matter sweeping past the sun's outer reservoir 100 million years ago. Most comets would barely notice. A few, including large ones like Bernardinelli Bernstein, might get just enough of a nudge to destabilize their orbits. At first, the effect would be subtle. A gradual change in distance at the far end of their path. Orbit after orbit, that small change would grow, until eventually one side of the ellipse dipped toward the giant planets, and the slow fall inward began. By the time we saw the comet, the dark matter clump would be long gone, leaving only its aftermath. There is also the galaxy itself. The Milky Way is not just a static background of stars. It has arms, a central bar, a disk of gas and dust, all moving and rotating. As the Sun orbits the galactic center, it passes through regions of slightly different density. Each region exerts a slightly different tidal force on the distant cloud. Over billions of years, those tides can pump energy into orbits, tilting some, stretching others. In that sense, the entire galaxy becomes a sculptor, slowly carving the outer architecture of our system. All of these ideas share one uncomfortable feature. They are hard to prove. Planet 9 demands a direct sighting, a pinprick of reflected sunlight moving just so. The massive disk concept demands detailed mapping of distant, small bodies far dimmer than most telescopes can see today. Dark matter clumps hide behind a double curtain. We cannot see the matter itself, and its gravitational fingerprints on a handful of comets are subtle and slow. Galactic tides are real, but their effects blend with all the other nudges acting on the cloud at once. So, astronomers play a long game. They build simulations that include different proposed sculptors, then ask which combination reproduces the sky we actually see. A model with no hidden players might produce too few steeply inclined orbits. A model with a heavy Planet 9 might produce too many. A model with granular dark matter might create distinctive clusters. Step by step, run by run, they try to narrow the field. Bernardinelli Bernstein is one of the test cases. If your invisible architect cannot produce a comet like this with the right orbit and timing, your architect is probably wrong. There is also a philosophical tension under all of this. We like simple stories. One hidden planet that explains everything feels clean and satisfying. A messy combination of tides, stars, clumps, and long-term diffusion feels unsatisfying, even if it matches the data better. Nature, unfortunately for our taste, often chooses messy. The outer solar system may be the sum of many small shoves, rather than the signature of one giant hidden hand. Yet even the messy picture is humbling. It means Bernardinelli Bernstein's path is the product of influences that span from the scale of undiscovered icy bodies to the scale of the entire galaxy. This one comet may have been shaped by a passing sibling star in the Sun's youth, by the slow pull of spiral arms, by encounters with giant planets, and maybe by forms of matter we still do not fully understand. Seen that way, Bernardinelli Bernstein stops being just a local oddity and becomes a messenger from a whole network of invisible forces. Which brings us to the strangest set of speculations of all. Because whenever people see patterns and hidden hands, a certain question eventually surfaces. What if the sculptor is not just gravity? What if something about this object is not natural? In the next part, we will step carefully into that territory and separate the science from the storytelling around artificial comets and engineered worlds. Whenever something in astronomy looks wrong, a familiar whisper starts to spread. What if it is not natural? Bernardinelli Bernstein is big, strangely tilted, oddly stable compared with skittish little comets. It is exactly the kind of object that invites late-night speculation about alien engineering and hidden probes. Those stories spread fast. If we ignore them, they grow teeth. So, the best way to handle them is simple. Put the wild ideas under the same bright light we use for everything else and see what survives. The first claim people point to is its brightness behavior. Many small comets flicker. As they rotate and vent gas from irregular surfaces, they brighten and fade in jagged patterns. Bernardinelli Bernstein so far looks calmer. Its light changes appear smoother, more regular, almost as if the object were a rigid constructed shell rather than a lumpy rubble pile. To some minds, that smells like design. Smoothness feels engineered. The physics answer is less dramatic and more satisfying. Inertia matters. A body more than 100 kilometers wide has a lot of it. It tends to rotate slowly and evenly. Local jets and surface bumps still play a role, but their effect on the overall brightness curve averages out. It is like comparing the wobble of a toy rock to the steady spin of a planet. The big one looks calmer because gravity and momentum are smoothing out the noise. Bernardinelli Bernstein does not need metal beams or alien control systems to rotate quietly. It just needs mass. The second favorite claim centers on the jets. Radio maps show that carbon monoxide gas is not leaking from everywhere at once. It erupts from specific regions that remain active over long periods. To someone already primed for an artificial story, that can look like exhaust vents on a machine, carefully placed and regulated. A natural comet, they argue, should be messy, with random patches turning on and off. Except that is not how real comets behave. Even small ones tend to develop persistent active areas where fractures cut through the crust and tap into subsurface volatiles. Once a vent is open, sunlight keeps it working, pass after pass, until the local supply is depleted or the geometry changes. On a giant with layered materials, those preferred vents become even more likely. The surface is not uniform. Some regions crack more easily. Some regions overlie deeper reservoirs. The result is a pattern that looks intentional but emerges from physics alone. A third line of speculation leans on the orbit. A path tilted by almost a right angle and tuned to skim just past the territory of the giant planets feels, to some, like a deliberate survey trajectory. The fantasy goes like this. An advanced civilization wants a slow, long baseline look at a planetary system. They send a hardened object in on a steep orbit that crosses the planetary plane, spends time near the giants, then glides back out, hide it in plain sight as a comet, and no one suspects a thing. It is a clever story, but it runs straight into both energy, costs, and evidence. Launching a 137-kilometer-wide probe would be absurdly expensive in any plausible technology we can imagine. It would require more material and energy than building entire fleets of smaller craft. An advanced species might not care about budgets the way we do, but basic efficiency does not disappear. If you can build star-spanning technology, you can probably design something subtler than a flying mountain of ice. More importantly, when we look at Bernardinelli Bernstein with the tools that actually test for artificiality, nothing jumps out. Its spectrum shows normal cometary ices and dust, carbon monoxide, likely carbon dioxide, water, organic molecules of the sort we see in other icy bodies, no obvious exotic alloys, no excess heat that would hint at internal machinery, no narrowband radio signals screaming for attention, just the blended hiss of natural outgassing. That does not mean it is impossible for a super advanced builder to hide perfectly. It means the hypothesis is not needed. Science moves by asking what simplest picture explains the data we have. So far, everything unusual about Bernardinelli Bernstein can be traced back to size, orbit, and history. A planet embryo that ended up in the distant cloud will have deeper volatile reservoirs, a rounder shape, smoother rotation, and more organized jets than a 10-kilometer ice shard. None of that requires guidance. Still, the artificial narratives tell us something useful about ourselves. Humans are pattern machines. When we see an object that breaks the rules we were taught, our minds instantly reach for intent. We imagine designers, missions, plans. That tendency is not a flaw. It is the same instinct that helped our ancestors survive by guessing at hidden predators and invisible motives in the dark. The danger comes when we stop there, satisfied with a story instead of checking whether nature already has a better one. In a sense, Bernardinelli Bernstein is the perfect canvas for these projections. It is distant, hard to image in detail, and complex enough that any simple model feels incomplete. The gaps between what we know and what we want to know are wide. Conspiracy theories and speculative tales thrive in those gaps. The responsible response is not to mock them or to accept them, but to keep shrinking the gaps with better data. There is also a deeper question hiding underneath the alien probe fantasy. How would we actually recognize an engineered object in the outer solar system if one were ever there? What signatures would be convincing? Unusual shape alone is not enough. Strange orbit alone is not enough. Even exotic chemistry can have natural explanations. We would look for clear thermodynamic oddities, tight band emissions, patterns in time that match computation or communication, and other fingerprints of sustained energy use. Bernardinelli Bernstein shows none of those. So the picture that fits best is still the weirder kind of natural. A giant hybrid world, built in the early days of the solar system, exiled to the distant cloud, stirred by forces that reach from nearby stars to the galactic tide, now slowly warming and venting under sunlight for the first time in countless orbits. That is already a wild enough story, without adding hidden civilizations into the mix. Yet, even as we reach that conclusion, one more twist waits backstage. The next round of insights about Bernardinelli Bernstein and its kin may not come from human intuition at all. They may come from artificial intelligence systems trained to see patterns in comet trajectories and outer cloud structure that no person could untangle alone. In the next part, we will meet those systems and ask what it means when a machine starts telling us where the next giant from the dark will appear. For most of the history of astronomy, the biggest limit was not imagination. It was calculation. You can write down the equations that describe a galaxy or an outer cloud full of comets. Actually solving them for billions of years of evolution is another story. Even our best supercomputers choke on full detail simulations of every ice grain and every gravitational nudge. That is where a new kind of tool has slipped into the story. Artificial intelligence AI. Astrophysicists already rely on huge numerical experiments. They simulate thousands or millions of particles under gravity, let them interact, and watch structure emerge. That is how we test ideas about galaxy formation, planet migration, and the long-term chaos of the distant cloud. These n-body codes are powerful, but they are also expensive. Running one detailed scenario can take days or weeks of supercomputer time. Exploring every combination of tides, passing stars, hidden planets, and dark matter becomes almost impossible. In 2025, a group of researchers tried a different approach. Instead of asking the computer to simulate physics step by painful step, they asked an AI system to learn the answers from previous work. They trained a neural network on the results of many large cosmological simulations and on real survey data. Over time, the network learned to predict how matter clumps and flows on large scales without having to recompute every interaction each time. The surprise was not just that it worked, it was how well it worked. Once trained, the AI could reproduce the complex web of cosmic structure with impressive accuracy while running 100 to 1,000 times faster than traditional codes. Suddenly, problems that were once out of reach seemed tractable. You could run whole libraries of what-if scenarios. What if the dark matter halo is clumpy instead of smooth? What if there is a hidden planet at a certain distance? What if stellar encounters are more frequent than we thought? Solar system dynamicists noticed and began to adapt the idea. They fed similar systems with everything we know about the distant cloud and its messengers, long-period comet orbits, arrival times, measured inclinations, positions and masses of the giant planets, models of galactic tides, all the heavy gravitational history they could encode. Then they asked the AI to learn the patterns and extrapolate. One question on almost everyone's mind was simple. Given the sky we see today, where should the next Bernardinelli Bernstein-sized object come from? The AI does not answer with poetry. It answers with probability maps. Regions of the cloud more likely to send giants inward. Directions in the sky more likely to host faint distant bodies on similar paths. Time windows when pulses of arrivals are more probable. In early experiments, the AI produced something unexpected. When it tried to match the known distribution of comets and strange visitors, it kept preferring models where arrivals did not trickle in at a steady rate. Instead, they came in waves. Quiet stretches, punctuated by bursts of activity spread over millions of years. That pattern was hinted at in old human-made models of galactic tides and stellar encounters. The AI saw it more clearly, and it connected that wave structure to objects with orbits, much like Bernardinelli Bernstein. The system also flagged odd correlations in the outer architecture. It pointed to subtle relationships between the orbits of distant trans-Neptunian objects and the parameters of the giant comet. Relationships so faint that simple statistical tests barely picked them up. When researchers dug into those hints, They found that some could indeed arise from a past gravitational interaction we had underweighted. Maybe a particular configuration of Neptune and Uranus. Maybe a distant passing star that our earlier models had treated too simply. This is the promise and the danger of AI in astronomy. It sees patterns we miss. It also happily invents patterns from noise if we are not careful. The neural network does not understand comets. It does not know what a cloud or a galaxy is. It simply adjusts millions of internal numbers to better match its training data. If that data is incomplete or biased, the AI will faithfully amplify those flaws while sounding very confident. So scientists treat its predictions the way they treat any new instrument, with curiosity and suspicion in equal measure. When the AI says that a certain region of the distant cloud should be denser, observers point telescopes that way and see if more objects appear. When it claims comet arrivals come in pulses, dynamicists check whether independent models and impact records on planets show similar rhythm. The goal is not to worship the black box. The goal is to use it as a fast scout, racing ahead to mark interesting territory that slower, more transparent methods can then explore. There is also a philosophical discomfort. Science has always been about more than prediction. It has been about understanding. A model that says Bernardinelli Bernstein exists and moves as it does is not enough. We want to know why. What forces shaped that orbit? What history carved that interior? AI systems are not great at the word why. They are pattern mirrors, not storytellers. Humans still need to turn those patterns into physical explanations that make sense. Yet the partnership is already changing how we see the outer solar system. By digesting huge archives of comet data and merging them with galaxy-scale simulations, AI models are teaching us that the distant cloud is not a static reservoir. It is a dynamic structure, full of clumps, gaps, and preferred directions that record the sun's wanderings through the Milky Way. Bernardinelli Bernstein is not a random exception dropped in from nowhere. It is part of that evolving pattern. As the comet approaches perihelion in the next decade, AI tools will keep refining predictions about its behavior. Will its rotation speed change as jets grow stronger? Will it fragment? How will its activity compare with what layered interior models expect? Each new observation will feed back into the networks, tightening their grip on what is possible and what is not. If this works, the next time a giant wakes in the outer darkness, we may have more warning. Not because we stared at every patch of sky ourselves, but because a machine trained on the story of Bernardinelli Bernstein and thousands of other objects quietly raised a flag and said, "Something big is coming from there." In the final part, we will pull all of these threads together. The invisible sculptors, the layered interior, the pulses of arrivals, the strange orbit. And we will ask whether Bernardinelli Bernstein is simply the latest member of a natural but wild family, or an early sign that the physics we use for the deep dark needs to be rewritten. Stand back from Bernardinelli Bernstein for a moment and look at everything we have piled onto this one object. A distant cloud that may not be quiet, galactic tides and passing stars, ghost planets and dark matter clumps, hybrid interiors and layered chemistry. Artificial intelligence systems searching for patterns we barely understand. At some point, the questions stop sounding like simple orbital mechanics and start whispering something deeper. Are we missing a piece of physics? Or are we just finally seeing how messy the known laws can be when you stretch them across billions of years and trillions of icy bodies? In 2025, one idea caught a lot of whispered attention. A young theorist suggested that inertia might not be quite as constant as we assume in very weak gravity environments. Inertia is the property that makes matter resist acceleration. In the physics we teach, it is tied directly to mass and never changes. The new proposal hinted that in regions like the outer cloud, where fields are feeble and matter is sparse, that resistance might shift just a little, not enough to notice around Earth, just enough to bend paths very far out. If that were true, comet orbits in the distant cloud would slowly drift in ways our standard models do not capture. A body like Bernardinelli Bernstein might end up on a steep, strange path without any hidden planet or dark matter clump at all. Gravity would still rule. It would simply play by slightly different rules at the edge of the system. That is the sort of idea that can make physicists both excited and deeply annoyed. Excited, because a small tweak that explains multiple puzzles at once is always tempting. Annoyed, because it tries to rewrite 3 centuries of successful dynamics in regions where data are thinnest. The pushback was fierce. Reviewers demanded hard predictions. Spacecraft in the outer solar system follow trajectories that match standard gravity extremely well once you account for tiny effects like heat, radiation, and gas leaks. If inertia really drifted out there, probes like Voyager, Pioneer, and New Horizons should have behaved differently. Most of their weird quirks have already been explained with conventional physics. There is not much room left for a hidden new term. That does not mean all radical proposals are wrong. It means they have to survive the same gauntlet as every other theory. They must make clear predictions. They must match existing data. They must outperform simpler explanations when tested. For now, ideas about variable inertia and modified gravity sit in a kind of quarantine. Interesting, worth probing, not proven. So, where does that leave Bernardinelli Bernstein? In many ways, still at the center of a giant sorting process. If models that use only known physics plus reasonable unseen masses can reproduce its orbit, timing, and behavior, then we learn 2 things. First, our tools are better than we feared. Second, nature can build planet-scale comets and send them inward without breaking any fundamental law. That alone is a big shift in how we imagine the outer solar system. If instead the object keeps defying expectations, the story changes. Suppose its orbit drifts in ways no combination of tides and planets can explain. Suppose its activity near perihelion is far more violent or gentle than layered models allow. Suppose the statistics of giants like this one continue to clash with every conventional population model. In that case, Bernardinelli Bernstein becomes evidence that something in our deep picture is off. Maybe not inertia, maybe not dark matter, but something. The job then is to pin down exactly what. There is a quiet humility in how many researchers talk about this comet in private. They will tell you all the reasons standard physics should handle it fine. They will also admit how often the universe has surprised them. We thought all planetary systems would look like ours until we found hot Jupiters and tightly packed mini Neptunes. We thought galaxies would behave under visible matter alone until they spun too fast. We thought the universe might coast or slow its expansion until distant supernovae said otherwise. Each time, reality was stranger than the neat story we had written. Bernardinelli Bernstein sits right at that boundary where confidence and curiosity collide. It is large enough, old enough, and distant enough that tiny discrepancies in our models can blow up into huge differences over time. That makes it dangerous to overinterpret. It also makes it uniquely powerful as a probe of long-term dynamics. Any theory that claims to explain the outer cloud must be able to produce something like this on the right kind of orbit. Any bold new physics that claims to tweak gravity must pass the test of leaving this object exactly where we see it. In the meantime, we do what science does best. We keep collecting data. We measure its brightness and spectrum year after year as it drifts inward. We watch how its jets evolve. We refine its orbit with every new observation. We feed those numbers into both traditional simulations and AI-driven models. We let different groups with different assumptions take their best shot at explaining it. We let time and evidence grind away the weaker ideas. No matter how that process ends, Bernardinelli Bernstein has already changed something important. It has shattered the comfortable picture of comets as small, simple leftovers. It has forced us to admit that the distant cloud can harbor bodies closer to dwarf planets than to ice balls. It has reminded us that the outer solar system is a dynamic battlefield shaped by forces that range from local planets to the structure of the Milky Way itself. When you look up at the night sky, you will not see Bernardinelli Bernstein glowing bright near the moon. Its journey is quieter than that, hidden in the reaches beyond Saturn. Yet its story is woven through almost every big question we can ask about our place in the cosmos. How did our system form? How stable is it really? What unseen masses share this space with us? Do our cherished laws of motion survive in the deepest dark? Some of those questions will outlive this comet's brief moment in our telescopes. Long after it has swung past perihelion and faded back into the black, its data will remain, feeding models and arguments for decades. Future students will scroll through plots of its orbit and light curve, not as curiosities, but as benchmarks. Did your theory of the outer cloud handle Bernardinelli Bernstein? If not, back to the drawing board. So, when you hear that a giant is slowly falling toward the sun, it is natural to think of danger. In this case, the real threat is to our complacency, not to our planet. Bernardinelli Bernstein is a reminder that the universe still has room to shock us with new kinds of worlds in familiar places. It asks us to stay curious, to keep questioning, to keep looking outward and updating our story as new evidence arrives. The next giant is out there already, somewhere in the cold. When it begins its own long glide toward the light, we will be watching with better telescopes, better models, and a little more humility, thanks to the strange, slow, massive messenger we are tracking now.